Okay, my friends, this should be very interesting. I'm going to have a real good time with this. They sent a craft very close to the sun to see what's going on with the solar winds. They call them elusive. They don't understand them. Well, let's see what they are. And I think I can show you exactly what they are. Now, they sent a probe in there that was trying to figure out what these particles are and energies and all that business. So we'll get into their research after I show you my research. Okay, my little friends, we are going to try to understand dark matter, particle theory, all of that stuff. Because there's a lot of new discussion about the standard model. It is not correct. Nobody knows what dark matter is. They can't explain gravity. They don't understand that the particles in space saturate space, which slows light down. Light does not travel the same speed continuously because there is no vacuum in space. So we're going to start right from the beginning. This is going to be very, very interesting. I want to show you this. I did this. Basically, I was in the Army for Nike Hercules missiles and so forth, and this was the paper I wrote trying to describe the fact that everything is a dipole, and actually the transfer of energy is from light to atomic vapor. It is atomic vapor. That is atomic vapor. All right, it's light. It is atomic vapor. Let's get into this. Okay, my friends, like I said, this is going to be interesting and kind of fun. Now, I am a researcher. I research what everybody else has already searched. And I might find something that relates to something else, and I did. Now, this is from 1996. They found mountains on the sun. I'm going to explain this to you in detail so you don't say, oh, that's impossible. Well, let's see if it's possible or not. Just take your time. Now, this is San Francisco. The sun is covered by mountains of hot gases, and they're swirling like crazy, that are less than a mile tall, but up to 40,000 miles wide. All right, so they're really scrubbing right on the surface of the sun. They're not really high up, all of these hot gases just swirling. They're fairly low to the sun, but they create huge magnetic fields. We'll look at that in a second. Now, this is according to brand new images. So let's do it one more time. The sun is covered by mountains of hot gas. So they see these swirling mountains of hot gases less than a mile tall. Now, the sun has mountains. These bumps are about 5 times the diameter of Earth, every one of these little bumps. And this is from the Solar Observatory. However, the mountains are only 1/3 of a mile high. So these are just little bumps about 1/3 of a mile high. And they use this special telescope. Here it goes now. Whoops. All right. Kuhn announced his results at the American Geophysical Union fall meeting. Before colleagues, he had a chance to study them. Or before NASA, which funds some of the solar physics research, could announce it with any fanfare. So they really never announced it, basically. Some of us have seen it for the first time today. I'm just very surprised at the results, said Ed Rhodes, a heliomicrobiologist at the University of Southern California. I don't think this is at all impossible. I think it's potentially very exciting. And it is, because that's what causes all the sunspots. All right, the images were captured by Michelson Doppler imager. Now listen to this. It's an instrument that can detect an object the size of a quarter at the edge of the moon. A bump the size of a quarter at the edge of the moon they can see, because it's going to have a little tiny lump to it. Now, so if they can see that, now what they did was, it's one of a dozen instruments carried aboard the Solar and Other Observer, a joint U.S.-European space mission launched in 1995. Now, the imager detected about 60 bumps along the curved edge of the sun. So the sun is like this, and they got bump, 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 bump all over, 60 of them. Now, listen to this. It says, because it only can see the edges, there are likely hundreds of mountains of gases on the sun. And these mountains of gases are not only mountains, they're actually physical bumps. And they can actually see. Okay, as I showed you in this article here, in 1996, they discovered these mountains on the moon, and on the sun, I'm sorry, and they said that I think it's potentially very exciting. Well, it is, because it has a lot of ramifications, a lot. Now, what happens on the sun, here it is right here, there's all of this turmoil. It's nothing different than here on the Earth. There's no difference whatsoever. As the Earth spins and scrubs through all of the stuff that's in space, and it is packed with things that crush against it. Now, the sun is so huge that it's scrubbing through space like unbelievable. As I will show you, we'll see the details in extreme detail. But it's so violent scrubbing that it's just liberating all of its electrons. And all that solar dust, the solar wind, they know about this stuff. They just, it's all, space is completely saturated with this stuff. Saturated. And here it is. It's everywhere. It's everywhere. It's everywhere. And we're on one of these arms spinning around a galaxy, the Milky Way, and heading towards the center very slowly, basically, according to time. But there will be certain areas we're going to hit that are going to be bumps, and at that point it's going to either impact our system strongly. In other words, our system's going to have to push through all this stuff that's in front of it, like this stuff, or the stuff won't be there and we just go flying through like a vacuum, there is no vacuum in space. Nowhere ever in any tiny little region of space is there a vacuum. Light is particles, dust is particles, debris all of this stuff is particles. Anytime you see glow, that means there's a particle hitting into another particle, liberating energy. All right, that's as simple as it gets. Okay, they really have no good explanation, but they did do a solar wind study and explains how the northern lights get bombarded with particles from the sun, and that's why at the poles where the field is coming out, that's where they are most illuminated. So they think that's a big discovery, but there's a much bigger discovery to this than that. Every 11 years, there's a solar cycle. And what that means is the sun's magnetic field goes through a period in which the South Pole becomes the North Pole. All right, the South and North Poles, they flip. Exactly what happens in light. Light is nothing more than exactly the same thing as that. As the North Pole charges up, it starts to push hard and it'll flip. And then the South Pole, which is uncharged, will start to absorb charges. So the one that's leading forward charges up and then it flips. Because it's so charged, it bounces back this way, and the weak one comes in front. And I can show that in our light experiments. It's very, very obvious. So they say that the solar flares are intense, the bright bursts of radiation linked to the stars' magnetic energy. Magnetic energy only happens when you crush fields with other fields, or you spin fields against other fields. That is magnetic energy, field to field. So they are linked to the star's magnetic energy. As these flare-ups shoot out into space, lots of that energy in the form of streams of charged particles travel towards Earth. They're nothing more than muons and photons and gluons and all these little bits and pieces that are just shot right out of the sun because it's so hot, and every now and then it'll hit a really nasty little chunk that's coming through space, a nice little dense spot, because it's nothing more than dense and weak spots in space. It's not homogeneous, not by any means whatsoever. You can see that. It's very, very obvious. That's not homogeneous. If you're coming through there, it's not too bad, but if you hit this thing right in this area, you got a problem. It's going to push back real hard and you're going to burn up. And we could be hitting one of those now. But if there's no real serious interventions, it appears that it's 11-year flop. Now let me show you that actually happening in light. All right, this is the particles, the smallest particles I have ever found. This is from an article from Fermilab. And this one here has no mass, but can get big and small. And this one here has all the mass basically, and it never changes. It's a fixed size. It never, ever, ever changes. It's like a bowling ball. This can go into showers, or it can go tiny into nothing. Now here it is here. This shows you how the sun, just assume this is the sun. All right, this shows the energy values. The sun is moving this way. And what do you see here? This is the particles that sun has to go through. So here you have the interacting pole, and here you have the non-reacting pole. All right, the north and the south pole basically. Now, this you can see is charging up because it has to push through and plow through all the particles in front of it. And then it will go, and that one will jump in the front, and it will start to push and expand itself. It'll gain energy. Now, it's an 11-year cycle on the sun, but on light, it's like spontaneous combustion, instantaneous on steroids. Now, how did this happen? How did we get that to show like this? First of all, we use CMOS to see it, which CERN is using that now too. And we focused through a Venturi and forced the fields to crush themselves. So these fields are crushed. The whites are crushed. They don't want to be together. They're, oh, get away from me, get away. And they are so squishy that through this tiny, tiny, tiny slit, which is so tiny you can't see it because there's just too much energy being given off, they had to crush these little bits down into tiny little pieces, and they zip right through there. The black ones couldn't get through, so they separated, and here they are. They want to be attached to that white desperately. That's what electricity is when the white reattaches to the black. When you charge up a battery, you're filling it up with these white particles. That's all you're doing. That's all. You're just forcing white particles in, so there's too many of them. They want to get around to the other side where the black particles are. You've separated them. And you force too many in on one side, so it desperately wants to get to the other side. And it will go right through devices and so forth. It depends on the intensity of the battery, how much resistance it will oppose, because this has to go through whatever device you have. So if you only have 10 volts and you need a 25 or 60 volts or whatever you need to drive something, and you only have 10 volts, you still got energy, but you don't have enough to drive the device. That's probably a little confusing, but it boils down to the colors. And the red is weak, basically, and you can't turn on an LED with red. It just can't do it. It doesn't have enough energy. But green, and green doesn't either. Blue does. Blue will turn on an LED and force it to generate energy. Okay, I'm not one for making unsubstantiated claims, so here is my substantiation. Now, you see that white strip right here? Those are LEDs. I just took this out of a fixture that was a big long LED thing, and I soldered in right into one of the LED chips that sends out the light. Normally light would come out of there, light emitting diode. Well, it's also a photodiode. It will accept light and turn it into electricity if you have the right frequency of light. So here we are at the ambient lighting turns that LED on because there's some high energy particles. Well, watch this. I cover it up, goes right to 0. I take it off, it goes up back to 0.01 watt. See, off. It's not, so nothing's hitting it now. Boom, up it goes. Now, what can I do with red? This is red laser. All right, you see the red? All right, now I'm going to go right here, right on top of that. Boom. Boom, 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 boom. Right on top of it, nothing. 0 extra volts. Watch over here. I'm right on top of it. See that? It actually diminished it. That's interesting. Huh. I must be shadowing it a little bit. Anyway, the red does nothing. 0. Forget the red. Not good. Now, what do we have here? Here's a green. All right, so now here we have the green. Green is a lot more powerful, but it's still not powerful enough. Watch. All right, I think you can see that. All right, here goes. The green, boom, right on there. Nothing. Right on there, nothing, 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 nothing. Now we go to the blue. Now we got a sizzler. This baby sizzles. Watch that thing. And as a matter of fact, I have to go above the 2-volt scale. I have to go up to 20 volts, although it's not going to go that high. It's going to go over 2 volts, though, which the meter won't read. Watch this. This is the blue. Boom! Look at that baby. 2.4 volts. You see that? 2.44. That's what I can get out of that with the blue. Nothing else will turn it on other than the blue. Now, that is probably because of the different types of metals that are in this. It's a CMOS. It goes both ways. Complementary metal oxide silicates will emit electricity if you put electricity in, and they will emit light. I'm sorry. I got confused there for a second. Sorry about that. If you put light into them, they will spit out electrons showing electricity. If you put electricity in them, they will spit out electrons as light. All right, so it works both ways. So what you need to do is get the correct types of metals in thin films so that when the light hits it, it absorbs all the different frequencies. Because right now, the blue and the green, we've got nothing, the red and the green, nothing at all. So all the other frequencies are just wasted. We need to be able to absorb all those frequencies just like we're absorbed now. Look at 2.44 volts. That's a lot of voltage coming from a light. This light here I've been using for years and years. And all of them here. And I haven't used even the electricity in the little batteries. So what we're doing is we're forcing electrons out. Now, when we put them into the shower mode like that, as far as what they say is a shower mode creates just tons and tons of electricity. Tons. That's what they say in the literature. If you can separate the black from the white, which we did, there's no question about that. Absolutely zero question. And then harvest it here and put it into our batteries, just like you do now. You charge a battery. That's all you're doing is putting that white in, but you're having a hard time. And everything heats up because you're just forcing things against each other, really forcing, bang, bang. This is doing it just with light. Boop, 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 boop. It's hitting with the black, and the white is just like fluffy. It just goes, it'll go wherever it's told to go by the black. And the black says, get the hell through that thing and go down and get absorbed so we can get some free energy. And that's what the laser says. Get out, get out, get out, get out, get out. And I said, where do you want to go? Go down in the battery, you idiot. Now, you see all the different colors? Those are different transition metal colors. Transition metals have different frequencies that they absorb. It's as simple as that. So you absorb them here, send them down through like a big bus bar, basically, because you should get some serious amount of energy there. It goes through a photodiode, which means one way. The gate slams back, so it tries to go back. Nope, only there. Now it's down in your batteries. Do anything you want with it. Run motors and pump water and run lights. And literally, you can do almost anything once you turn it into electricity. And you can carry this around with something like this. What I just showed you with these lasers, creating this amount of energy right here, you should be able to put hundreds, if not thousands of those in there. Carry this around like this and just plug in whatever you want into it. It can be regulation. You can do 220 volts, 110 volts, 50, 60 cycles, USB, AC, DC, MOC, whatever you want. And carry it around with you. That's a big, big improvement to what they want to do with fusion, make these gigantic machines, and all you got to do is get one missile from somebody that doesn't like you, and you lost everything you thought you had. And fusion's never going to work anyway, because they have to put more energy in than they will ever get back. The only way to do it is basically the way we're doing it, is to divide the light. That's where they want to get down to, is the light anyway. That's all they're harvesting, is these white particles. That's what fusion does. It doesn't do anything special. You want to get this. Only they're getting them as heat. And I'm going to tell you right now, that is heat. The black is cold, the white is heat. The black literally is absolute zero. When you take every single electron out of superconducting materials, they're at absolute zero. At the absolute zero almost, because they can never get to absolute zero, because there's always going to be a couple of free electrons in there. But that's a couple of these little white ones are just going to be in there. But it's so cold and it's so black that it's a superconductor now, which means as soon as I touch it with electricity, boom, it says, give me everything you got, baby. And it will go flying through there. But all of a sudden it starts to resist. That's how electricity works. It's flow and resistance. Resistance causes heat. Heat is just nothing more than excess electrons. That's going to be hotter than hell, but it's only for just instant like that. Before we go back to the article, this is what I say. This is the sun. The sun is being ripped on one of these arms of the Milky Way, and we have to follow the sun. I'll show you how we're trailing the sun. And it's spinning tighter and tighter and tighter and tighter and tighter and tighter and tighter. And that's what causes a black hole, because it's forcing all the black particles to the center and all the white particles to the outside. That's why they're so brilliant in the core of a galaxy. But we are somewhere out here. We have to come through whatever is in front of us. And I'm going to tell you, there is a hell of a lot of stuff in front of us. And they should have known this forever. And this is what is happening to our atmosphere right now. 100 degrees or so on the surface, 2,000 plus out here. How did that happen? And then guess what? Just below that, it's minus 80. How did that happen? Tremendous amount of interaction between this scrub zone and our glued zone, which is considered our ionosphere. That is like a layer around our Earth. The religious people would love to call it the firmament, because it is. It is a literal layer around our Earth that these other particles are trying to get through, and it's a scrub zone. And that's where all the heat is out here. And not only that, the light that is out here is light as particles, and once it gets past this ionosphere into our atmosphere, it condenses. What happens to condensed particles? They turn into water. It separated the water above, which is the particles of light, from the water below the ionosphere. Here's your firmament, if you want to call it that. So out here, it's millions of degrees away from the sun, 10,000 on the sun. Our Earth is 100. Out here, it's thousands. The only explanation is the scrub. And here's what we do through the universe. We scrub. You see that? This is the arm of the Milky Way. The sun is just getting scrubbed. You see the scrubbing off of the sun? And we have to trail through all these particles, in addition to all the particles that are coming at us on that arm of the Milky Way. So, what they found, I don't know. We're going to know in a minute here, but I can tell you this is what is happening right now. This is the solar wind. That is the windy particles, the sandy sort of gritty things that are coming off of there that are actually particles. And John Glenn saw them, and I'll show you that in a second. That is what we have to go through. That's the solar wind. Now, in addition to that, of course, obviously, there's light. There's all kinds of light particles coming off of there in every different frequency and every different part of the spectrum. So we only see the colors that we can see, and those are the colors that bounce back at us. All right, there's all kinds of other colors, infrared and ultraviolet and so forth. You can't see those. They heat, they burn, they do other things, but we have the ones that bounce just at the right frequency that we can see all these colors. And every single thing that you see is a tiny little electron particle coming at your eyeball to stimulate a little receiver, just like it does a pixel on your phone or your camera phone. It's a little bit of a luminosity. Beep, it hits it, and the pixels can say, how hard did you hit me? What color are you? Your eyeball does the same thing. All kinds of other frequencies we cannot see. Those are heat and gamma rays and ultraviolet and the microwave radiation, which is very, very short frequencies are everywhere in the universe. And that's the other thing they can't explain. They call it the microwave background. Well, what is it? It's just light that's slowed down. It's just not hardly moving anymore. It's very, very, very slow light. Because it's just barely drifting around. This red shift is not a shift because things are being pulled away. It's a shift because everything coming at us is being slowed down. We have to force our way through everything in front of us. Light is not a continuous speed of 186,000 miles a second. Absolutely not. They know this for a fact now, but they disregard it. Just disregard anything that doesn't fit into their scheme. Very, very disconcerting. I'm going to tell you that right now. I'm having a very hard time with science. Okay, I'm going to try to make this quick because I know people don't have much time, but this is my new electron dipole flood theory, which says that everything is a dipole, and the way the nucleus is actually constructed is it has a dark core, and then the electrons surround it, and then more electrons want to get in, and these electrons say no, because they push the field away, and they keep extra electrons at a distance because they want to get in, but these push them away. They won't let them in. All right? Because they're just nothing but white particles. And that's what heat is, that's what electricity is, and that is what coats everything there is because it's so desperately attracted. It's the strong nuclear force. It's held onto that nucleus it won't release itself until they do these gigantic colliders at CERN and so forth. And we did it just by putting it through a Venturi. That's how we release the black from the white. Now we're going to go into this, but this is my electron flood theory, and I'm going to go through everything, what the particles are, what the nucleus is made of, and this is what CERN did. They upgraded to CMOS, the same thing we're using, and then they upgraded to focus, the same thing that we did. And as a matter of fact, I went to the University of Geneva, and I told them, well, we did this stuff, and then they shut down for 3 years and installed that stuff. Whether I had anything to do with it, I don't know, but they were pretty interested in my particles. What changes in the standard model? Well, quite a bit, but not a whole lot. It's kind of tricky. They missed a whole layer of electrons, that's all. And then it really affects everything, but it's because they missed one whole entire layer of electrons, which coats the dark portion of the proton. Proton's not just positive. It's dipole, but all the dark goes to the center and then the white surrounds it. That's why white bounces back at you. We see it as light. It's always in the inside. The dark will not absorb, it doesn't emit, and it doesn't reflect. So you hit that thing, when it says it doesn't absorb, it will coat with electrons, but it won't take them into itself. All right, and it won't emit them. They don't bounce back. The only ones that bounce back is the white ones. When a white hits another white, it bounces back. That's a white hitting white. The black just bangs into everything else, and it doesn't emit any light, it doesn't absorb any light, and it doesn't reflect any light. And the only way we could see it is because once we exploded them, the black is laying on top of the white, so we can see the black on top of the white. You never see that because everything else is big, big balls like this. And the black is always, 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 always on the inside. Everything you see here, 100% of everything you're seeing is completely painted with white particles. There is not a single thing here that you can see the blackness. That's why it's dark matter. You never saw it because it's on the inside of everything. All right, we're talking about tiny, 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 tiny atoms. And every single proton is coated with electrons. So you can't see inside, you can't see the dark matter. But it's there, and it's the gravity, and it's the weight. The white has virtually no weight at all. And I've shown this so many times, it's time to pay attention, because we might be able to get free energy. And anyway, it's all dipole electron flow theory. So we're going to hopefully get somewhere with this, and it would be fabulous if we could get something like that, where we could walk around with a little device like this and plug anything you want into it. And have all your stuff inside here. And that should be it. Alright, that would be nice to be able to walk around with something like this and have all your voltages, just plug it in. War zones and stuff like that, which seem to be pretty prevalent nowadays. You could at least have some electricity for yourself and keep lights on, do all kinds of stuff with that. And you should have a ton of electricity out of this, if they're right. Because here's what they say. Not my words, this is their words. Nope, I'm sorry, that's about the sun. Here's right here. Electron showers, exactly what we did. The neutrinos are from the electron showers. And they go from a few hundred gigavolts to a few trillion volts, electron volts. And that's exactly what we did, was we created electron showers. I got it, oh, here it is, right there. You see, they were here together, the same thing. And remember, we started out talking about how the sun is going to spin every 11 years. It's because they charge up, spin, that one comes in front, absorbs. So I think we got past that. But here's where we have our electron showers. If they're right about the values, we're into the stratosphere with electrons. We're going to have more electrons than we can ever use, because we separate them completely from the black. It's almost impossible to do that without really putting a lot of energy in. When you charge something up, you had to put that energy in. All we're doing is hitting a certain tuned device that forces fields to collide so much that they drive off the electrons of everything else that's in front of them, and they create the shower. So instead of having one electron, you got thousands of them now. And then you can just funnel them down, because they're just nothing more than fluff. Once they get past this Venturi, they're just fluffy little things. And you could just drive them right down into a harvester. I believe, again, I cannot prove this. I can't prove anything of well, I can prove what I'm showing you here. There's absolutely no question about that. But will we get free energy? I don't know. The way the claims are, yes, we should get at least 200 times. And if they're talking billions or trillions of electron volts, we're only using probably, mega electron volts tops. Like I say, I run these lasers for years, 5, 6, 7 years now. Same batteries. So how much electricity did I use? When you see this, that's just stunning amount of electricity. So I'm hoping we can get somewhere, but I need somebody to step up. I can't do it. I am done out. I'm at the end of my doneness. So somebody's going to have to step up and help. All right, thank you. Okay, my friends, this just came out moments ago about breaking news. Physicists detected the background hum of the universe. Well, is it humming? I don't know. But what they're looking at here, they're talking about gravitational wave astronomy, relatively new field. Well, they're still really sort of missing a lot of stuff, which I will show you, following the detection of space-time ripples caused by 2 colliding black holes in 2015. You don't need to collide black holes to make space-time ripples. All they are is magnetic fields, because anytime you bang something, it goes boom, 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 and it slows down. I will show you this. Since then, Earth-based gravitational wave detectors picked up nearly 100 confirmed gravitational wave events at the time of this writing, all created by mergers of compact stellar mass objects, black holes, and neutron stars. Well, maybe. Maybe they have something they're seeing that I don't know about, but I can show you what we can see, and I will right now. All right, they're talking about gravity waves. Well, what do you see here? These are nothing more than magnetic fields. And you see how tight they are down there? When something is just got banged, it pushes out, but then it hits something else and it pushes back a little bit, and then it hits something else and it pushes back. So it's boom, 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 boom. You see it? and then it stops because it can't force its way through all the other particles anymore. Light in space is slowing down very, very fast, which means that none of this measurements are talking about hundreds of billions of light years. It's insanity. What is all this? They're all dipoles. Everything here is a black and a white. Look at this one. Now this stuff is right. This is on top of the moon. This is the moon, and the moon doesn't have a magnetic field because it's not spinning. It's pushing. You see how it's pushing the white light and forcing it to concuss, which gives it a blue hue, and the trailing edge is where it's reddish. All right, so if it was spinning, you'd see this kind of a field. Wherever that spinner is, apparently it's behind the moon somewhere there. It's spinning like crazy and creating this huge field. All of these particles here in space, which are moons or suns or I don't know what they are, but every single one of them has a pretty serious field. So we know that light is not going to come through space as the speed of light forever. It's the same speed. It slows down very, very, very clearly. I have shown this in so many ways. It's just incredible. Light slows down very, very simple to see it. Here it is right here, slowing down. Came in hot. It's slowing down. That's blue. Blue really comes in hot. See how tight it is here? And light is nothing more than a spinning particle that has to concuss with everything in front of it because it has a field. So that thing there, think of this. It's got a field surrounding that particle. It's just going just like this. And when it comes in real fast, it's going. It's going to shift towards the red. Eventually, it won't have any more speed left to it, and it becomes what they call a cosmic microwave radiation background. It's just floating around basically because it's worn out its speed. Light slows down. I mean, there's just no question about it. And it speeds up too. And not only does it speed up in a vacuum, it speeds up inside of the room in an air which is saturated with gases which all have their own fields. You see that? That's nothing more than light. It's pulse lasers. It goes the same speed as every light. They say it can make no difference whatsoever. Well, I can tell you what. That's right now beginning to accelerate. And still, even if it doesn't accelerate, it has to push through all the particles in front of it to get to where it bangs into something to bounce back as light. As they're going forward, you don't see it. You don't see any light here. But when it hits something, it bounces back. You don't see any light right here. Right? You see this? You see any light hitting this? No, you don't see any light hitting that. But there is all kinds of light hitting that. If I turn the lights off, it goes dark because there's nothing bouncing back. Light is bounce. All it is bounce. It's like this particle coming down, hitting me and going boing, and when it comes back out, I see it as the color of my skin. As simple as that. And you will never see anything of the dark particles because they're always inside the white particles. The white surrounds everything. I hope I've been clear about this because I've been saying it over and over, and I want somebody to pay attention. And actually, I put up a paper on academia.edu the other day, only a couple of days ago, and I already got, for a paper, it's got a ton of hits, like 60 hits or so within 2 days. That's for a scientific paper. That's a ton of hits. So I'm hoping it'll keep going. Anyway, it's on academia.edu. It's called, hold on one second. Hold on, let me find it. All right, here it is right here. 63 views on dipole electron flood theory. DEFT, dipole electron flood theory. And that's up on academia.edu. And it only was up there for a couple of days. That's a lot of hits for a academic paper. It really is. Most people don't read these at all. But this is a complete change. And it has to be taken into account. And I'm hoping these people will. I've already got it locked down that I discovered the dipole electron flood theory. And if you don't put something up and have documentation that you would have wanted to figure it out, trust me, somebody's going to take it and say, I figured this out, I was the one. I've had them say the stuff all about my research for years. Every time I do something, the next couple of days later, somebody figured it out 10 years ago, you know. So that's the way it works. Anyway, it changes everything. Changes everything. Okay, I'm sure I've already spoken about, or will speak about, the scrub between our outer atmosphere, which is basically sort of glued to the Earth, but we're spinning like crazy, being dragged through the arms of the Milky Way, and we have to scrub through all the particles in front of us, and there are a ton of them. It's not vacuum, nowhere near a vacuum. So we keep scrubbing this. Now, what would happen if we blew up that atmosphere? We would scrub harder. What would happen to the atmosphere? It would get turmoil. And what does that mean? You'd have tornadoes, you'd have hurricanes, you'd have floods because you'd have more condensation. You'd have a lot of really heavy-duty rains, inches and inches and feet, which they're having now. You would have extreme amounts of extremely heavy hail. Why would that happen, Roger? Well, let's think about it. You're concussing crazy. You're not here anymore, you're out here. And all these fires up in Canada and places like this, it's just expanding the atmosphere like unbelievable. Every time you burn something, they call them greenhouse gases. Yes, they're combustion gases. It means you break something down from a solid state into molecules of gases. You got literally thousands and thousands and thousands of expansion times. So what does that mean? We're scrubbing harder and harder and harder. It's as simple as that. So what does that mean to our atmosphere? It's getting hotter and hotter and hotter. That means it's getting hotter down here. It doesn't try to leave. It's being pushed in. That's what they're missing with global warming. It's not that the stuff just can't get out. It's being pushed in. I don't care how much carbon they take out. If they don't take out the gases, it's all over. They got to take out the carbon dioxide. Then you could shrink this stuff down. But burning stuff, you're just filling it up. And that's what's happening up in Canada. And the Earth is getting more and more turmoil. Now, let's think about the hail. Because that's something I have to explain too. I have to explain 100% of anything that anybody can bring to me about any material event whatsoever. Now it's at that point now where I have to explain every single material interaction. How did this goose, Caesar Augustus, how did his feathers turn into stone? How does light travel? How does it react? How does it bounce? Where is dark matter? What's the basic construction of the universe? Every bit of that I can explain now, and that's what I want. And it's not bragging, it's just true. So I want to talk to somebody about this stuff. That's what I expect. Here's why we're having such extreme amounts of big, heavy hail. Some of them baseball size. That'd kill you. It's compression creates rain. All right? High pressure. It crushes the water molecules, the H's and the O's, and it turns to H2O, and it rains. Now, out here it's hotter than hell. It's 1,500 degrees Celsius out here. That's 2,700 degrees. And we're spinning and pushing, and it's crushing down. Well, if it got bigger, it would keep push harder and harder. Down here, just below that range, is minus 80 degrees Celsius. That's 112 degrees below zero. Now, so normally you don't get hail coming out of here because it's not crushing it hard enough. But now it's crushing it so hard that it's condensing way up here instead of down here. Usually it condenses down a little lower and you get the rain coming down there. Up here, you get hail. It's condensing up here instead of down here because everything is crushing so hard. And then all of the atmosphere on the Earth is just, and it's not going to get better. They're flying in the area where it's going to be. Right now, they had to cancel all kinds of flights the other day because it's too much turmoil. And I don't think it's going to get much better, my friends. I'd be looking at some serious amount of trouble in flights if this continues. And I don't see any way it's going to slow down. But I could be wrong. All right, see, this is the BBC. They did basically what we've been doing. This didn't come out that long ago, and basically that's what we've been doing here. This is with a screen, and you can see, and you know, they might have some better equipment than us. We only spent a couple $100 on everything we did. And this is the one coming out of, this is literally a black hole. They made charged particles in zero gravity in a vacuum chamber. It created a black hole. They went insane. During the experiment, we contacted the Earth guys. They couldn't believe it either. Nobody believed it, because the black can remove itself from the white. I never thought that was possible either. But it appears to be quite obvious now that that's true. And the white particles are strictly the electrons. That's what I'm seeing now. And these electrons are all kind of collecting around the dark particle, because that's the gravity. This freaked everybody out. I showed you the BBC shot. Well, this is just with a red laser, not a screen, just one single slit. That gives us the opportunity to know that it is a spinning disk, and it spins this way, just like a drill bit. It spins this way, and some of them go through that direction, some of them come under and go through this direction. And they're all over the place. So some of them come way out here, and some of them come right straight through the middle, some of them come over here. Hold on a second. Okay, my friends, as I showed you, I don't think we're going to get a lot better quick unless we do something about expanding our envelope of gases. And we're seeing this extreme amounts of turbulence everywhere in the world. It's not just here. But it's really very, very, very bad now, and it's going to get worse. I can't see it getting any better. Now, they had all these people stuck on planes. They couldn't fly because of this weather. And again, I'm hoping it won't be as bad as I'm forecasting, but it could very well be. We need to cut back on these expansion gases. They call it greenhouse gas. I don't care what you call it. Gases expand our footprint tumbling through the universe. It's as simple as that. It's not a hard concept to understand. We're being scrubbed to death. That's why it's 2,700 degrees way outside our atmosphere. Why? It's because our atmosphere is scrubbing the other atmosphere, which is what they call a vacuum of space. It's nowhere near a vacuum. That's where all the interactions happen. And the bigger our expansion, the scrubber it gets. The scrubber it gets, the hotter it gets. The hotter it gets, the more compression and scrub and push on the atmosphere, and condensation and turmoil. And especially where you have mountains and hills and valleys and so forth, they just flop around like that while they're getting turmoiled up. And that's what's happening on the sun. The sun has little mountains on it. That's what all the solar flares are all over the place. And they're getting more interacted every now and then because they're pushing through denser space every now and then. I believe that's as simple as it can possibly get. So anyway, I'm going to be presenting again my electron flood theory. It changes everything. I mean, it changes everything as far as we think about space and the nucleus and heat and light and virtually everything. Chemistry even. Biology. You can't make biology work with this. There's no way in the world you can make biology work with that. There's a ton of different isotopes and enzymes and all these things that use this type of chemistry, but there's so many isotopes and variations of these particles, because now they're not just one or two or three big balls called protons. Every one of those balls is a dipole, and it's about 1,823 dipoles. So now you really got some work you can do with that stuff. Otherwise, you just got a couple of big balls rolling around. That's not going to provide life. So as I said before, nothing stands alone. It's not like we got a new atomic model, that's the end of it. No, it covers everything, baby, everything. All right, you saw how fields interact. When they push and shove and bang against other particles, they glow. Well, this is what's happening to us. The sun, we're all being dragged through the arm of the Milky Way. We're trailing the sun, which is the leader that's pulling us behind it, and we're spinning and it's sloughing off all kinds of stuff. This is what happens in space. This is our solar system on an arm of a Milky Way. And these are all the planets following the sun. The sun is pulling us. And, you know, we're also being dragged by the arm of the Milky Way, but the sun is is out in front of us. And we have to plow through all these particles. All right, so we got some serious particles coming at us. Now, is it just the dense out here and this thing's hitting more denseness, so it's really splaying all kind of crap at us and fields and so forth? Or is it just that we're getting so big that the same stuff out there is now really impacting us? It's one or the other. And we are blowing up like a balloon, especially this stuff in Canada with all these fires. And I think this happening in a lot of places around the world. I'm not certain of that, but I certainly know Canada is a major contributor at this moment.